Your thought for the day. We're going to cover 4.1 and 4.2 today. So 4.1 is apply triangle sum properties, and 4.2 is apply congruence in triangles. Our objectives for 4.1 is classify triangles and find measures of triangles' angles. Definition: a triangle is a polygon with 3 sides. Triangle, 3-sided polygon. Vertex, or vertices, is the plural of vertex. Each of the points of a triangle. It's where the sides meet. A triangle's 3 angles add up to 180 degrees. Simple proof of how we know they add up to 180 degrees. If I take a triangle, so I have this triangle, and I tear it into 3 parts. So each part has one of the vertices in it. And then I put those vertices next to each other on the piece of paper. So there's one vertex. There's a vertex. I take the other vertex and put it there. And here's my third vertex. Those 3 vertices, it's kind of crooked, but there. Those 3 vertices, when I put them together, they make a line. So that's 180. True of any triangle. Types of triangles. Okay, if we classify them by the sides, one type of triangle is an equilateral triangle. Means equilateral means sides, so it means all 3 sides are equal in length. Equilateral triangle. Three congruent sides. We mark each side with 1 tick mark to show all those sides are the same length. Isosceles triangle. An isosceles triangle has at least 2 congruent sides. You can see in this shape, these 2 sides are congruent. The third side is different. It's isosceles. All equilateral triangles are isosceles triangles. They just have an additional congruent side, but you just need 2 for an isosceles triangle. Then if none of the sides are the same, we call it a scalene triangle. No congruent sides in a scalene triangle. If we classify a triangle by angles, if none of the angles are the same, then if all the angles are less than 90 degrees, which is acute, then we call it an acute triangle. This is an example of an acute triangle. 45, 55, and 80 are all less than 90 degrees, so that would be an acute triangle. A triangle with a right angle is a right triangle. No triangle can have more than 1 right angle. So one right angle in a triangle is a right triangle. And when we label a right triangle, the sides that are next to that make the 90-degree angle are the legs. The side across from the 90-degree angle is the hypotenuse. Obtuse triangle. An obtuse triangle has one obtuse angle. One angle greater than 90 degrees. There's an example of an obtuse triangle. It has a 130-degree angle, so it would be considered obtuse. You may be asked to, they ask you to classify a triangle, classify both its sides and angles. So you could, like, for example, you could have a right scalene triangle. This picture of the right triangle, this would be a right scalene triangle because none of the sides are the same length. It's possible to have an isosceles right triangle. And those type of things. You could have an isosceles obtuse triangle. So you classify it by its sides and by its angles. Okay, now classify this triangle in the coordinate plane. It says classify it by its sides, then tell if it's a right triangle. Let's focus on the sides first. What can I use to determine if it is what it is by its side? What would I use? Yes? Right, we're going to use the distance formula. So we can do the distance formula is distance is equal to the square root of x2 minus x1 squared plus y sub 2 minus y sub 1 squared. So we can do from P to O. P to O would be the square root of x2 is negative 1, so we have negative 1 minus 0 squared plus y2, we would say 2 minus 0 squared. And then we simplify, so that's the square root of negative 1 squared is 1, 2 squared is 4, so it would be PO is the square root of 5. Then we're going to do the distance from Q to O. Everybody have that? Okay, so distance from Q to O would be the square root of 6 minus 0 squared plus 3 minus 0 squared. So that would equal to the square root of 6 squared is 36, 3 squared is 9. That would be square root of 45 from Q to O. Then the last one we have to do is from P to Q. Go ahead and do that one yourself. Do the distance formula from P to Q yourself, and then we'll compare the distances. should have gotten the square root of 50 from P to Q. So given those distances, what would we classify this triangle as? Yes?
It would be a
Scalene, right. This is a scalene triangle. All the sides were a different length. Okay, what about the right triangle? How can I show if it is a right triangle? What would I do? What do we need to compare? Trent, what do we need to compare to determine if it's right? Taylor?
PO to OQ.
Well, what about those lines? What are you comparing, though?
You're adding them together to see everything.
We're not adding them. We're going to find the slope of both of those lines. We're going to find the slope, and the one that do the one that looks most like a right angle. Like she said, PO and OQ look like they may be 90 degrees. So we need to find the slope of PO and the slope of OQ. So we use the slope formula. M equals, so y2, we'd make that 2 minus 0 over x2 would be negative 1, x1 would be 0. So it's 2 minus 0 over negative 1 minus 0. So we get negative 2 is the slope for PO. Let's do the slope of OQ. Slope of OQ is equal to 3 minus 0 over 6 minus 0. That equals 1/2. Are those lines perpendicular in Y? On.
Yes, because they're opposite.
Right. They are. I forgot my negative. No, I didn't. There's a negative 2. So, yeah, 2 and 1/2. We flip the 2, it becomes 1/2. We change the sign, it becomes positive 1/2. They're opposite reciprocals. So that is, we could say it is a right triangle. PO is perpendicular to OQ. So it's right. All right. This is all the work. Angles. When angles of a polygon are extended, other angles are formed. Exterior angles are angles that form linear pair with the interior angles. In this picture, all these angles that are marked with the squiggly are exterior angles. They make, so I take an interior angle. This is an interior angle. And I combine it with this angle. They make a line. Right? It forms a linear pair. So that squiggly, that angle is an exterior angle to the triangle. But not all the angles outside are exterior angles. This angle, right here, is a vertical angle with this angle, with the angle inside the triangle. Vertical angles are not described as exterior angles. They are vertical angles. So the exterior angles are just the ones that make the make a line with the interior angle. At each angle there are two exterior angles, one on each side. Interior angles, it's the angles inside the triangle, the original angles. Yes?
Wouldn't Wouldn't those be exterior angles too if they're not in the actual triangle?
This angle?
Yes.
That's a vertical angle. Vertical angles are not considered exterior angles. Even though it is exterior, but just the way we define the exterior angles, that is not considered an exterior angle to this triangle. Just the angles that make a linear pair with the interior angles. Corollary is a statement that can be easily proved using a theorem. So we've got a couple theorems here. The triangle sum theorem. Triangle sum theorem simply says that the angles of a triangle, the interior angles of a triangle, sum to 180 degrees. 1 plus 2 plus 3 equals 180. The triangle sum, the exterior angle theorem. The measure of an exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. So the exterior angle we're talking about is 4. Non-adjacent means not next to, so that excludes 3 for an interior angle, but 2 and 1 are interior angles. If I take angle 1 and angle 2 and put them together, they're going to equal angle 4. Those are the non-adjacent interior angles. Their sum equals the exterior angle on the other side of the triangle. And that makes sense because if you think about it, 3 and 4 are a linear pair. We know a linear pair adds to 180. So 3 plus 4 equals 180. Triangle sum tells us all 3 angles add up to 180. So 3, we also know that 3 plus 1 and 2 equals 180. So 1 and 2 together make 4. Corollary to the triangle sum theorem. We know that in a right triangle, the two acute angles are going to sum to 90. If one of the angles is 90, for the triangle to equal 180, the other two have to equal 90. We know two angles, when you add them together, are called complementary. So 1 and 2 in this case would be also equal to 90. Do I have it? All right. Find the angle measure. We have to find a measure of JKM. How would I set this up, and how do I know to do that? How would I set it up? Kayla.
You would add 2x minus 5 plus x equals 180.
You got the right idea, but you didn't have the right combination. Lindy.
Is it x plus 70 equals 2x minus 5?
Right. X plus 5, 2x minus 5 is the exterior angle. These two are the non-adjacent interior angles. Their sum, x plus 70, equals the exterior angle, equals 2x minus 5. And then we solve, so we would subtract 2x from both sides. And we get negative x, and then plus 70 equals negative 5. Then we subtract 70 from both sides, and we get negative x equals negative 75. So x equals 75. We have to find JKM, so we have to plug in 75 into 2x minus 5, so that'd be 2 times 75 minus 5, that's 150 minus 5 is 145 degrees, would be equal to angle JKM. All right, everybody have it? Next slide. Okay, we're on 4-2 now. You guys want to take a break? Or you want to push on? Take a quick break? What's that? Just keep going? Okay, 4-2. Apply congruence and triangles. Our objective is to identify congruent figures. In two congruent figures, all the parts in one figure are congruent to the corresponding parts of the other figure. In congruent polygons, this means all the corresponding sides and the corresponding angles are congruent. For a triangle, that's 6 parts. All 3 sides that correspond have to be congruent, and all 3 of the angles that correspond have to be congruent. Now, this corresponding part is important. What we mean, we'll talk about with corresponding here in a minute. Let's talk about notation. The dash marks show which sides are congruent. In this triangle, AB is congruent to EF. AB would correspond with the EF in these triangles. They're congruent. BC and DE are both congruent. They correspond, and AC and DF are congruent. They correspond. So that takes care of the 3 sides. And then the angles. You put the same number of arcs to show they're congruent. D and C would correspond. B and E would correspond, and A and F correspond. When naming angles and sides, you start with 1 and move around the triangle clockwise or counterclockwise. So in naming these 2 triangles, let's start on the triangle on the left. We're going to name it, let's call it triangle ACB. If I call this triangle ACB...
Can we go back a slide? I can't read any of the dash marks or any, I don't know what any of it says. Or not say, but I can't tell how many marks there are.
Okay, I'll mark it with my pen.
Okay, thank you.
AB is congruent to EF. BC is congruent to DE. And AC is congruent to DF. That takes care of the 3 sides being congruent. Then for the angles, angle D is congruent to angle C. Angle E and angle B are congruent. So I put 2 arc marks. And then angle A, 1, 2, 3, is congruent to angle F. 1, 2, 3. 3 marks for the angle. These 2 triangles, we could say they're congruent because 3 corresponding sides and 3 corresponding angles are congruent. Now, let's get this corresponding part down. If I name this triangle ACB on the left, let me mark it. Since you can't see the markings, I'll put the markings in. if I call this triangle ACB, when I name the second triangle, I have to find the angle that corresponds with A. What angle corresponds with A? Yeah, it's D. It has one mark. So that would be D. And then what angle matches up with C? Yeah, it would be E. They both have 3 marks. So it would be D, E, and then the B goes with F. If I name this second triangle FED, then I couldn't say they're congruent because the corresponding parts, as I've named it, aren't congruent. So you have to make sure you name them with the congruent parts corresponding to each other. Let's name the triangle a different way. Let's call it BCA. If I name the triangle on the left BCA, what would I name the triangle on the right? What corresponds with B? F. So the first letter would be F. What corresponds with C? E. And what corresponds with A? D. F. So it would be FED. Let's try another way to name it. If we called it triangle CAB. What would be my first letter in the triangle on the right? E goes with C, so it would be E. What goes with A? D. And what goes with B? F. Everybody get the idea on naming triangles? All right. Third angles theorem. If 2 angles of one triangle are congruent to 2 angles of another triangle, we don't have to calculate the third angle. We automatically know they would have to be the same. Right? If 2 angles are congruent, then the third one's going to be congruent because we know it's going to add to 180 in both triangles, and whatever it takes to add to 180 would be the same in both triangles. Here's an application of that theorem. So it says find angle BDC. Alright, so if I'm going to find BDC, first of all, as marked in the figure, what can I say about the angles? Yeah, we've got some congruent angles. So we could because of the markings, I could call this angle 30. And I could call angle B 45. So let's draw these separate. They're overlapping. We're going to separate them. This is ADC. This is the 45. And this is the D would be 30. Right? And then the other triangle would be B, D, C. And in that triangle, this is 45. Come on. This is 30, and this is 45. All right. So, let's calculate. Oh, this is not A. That's BDC. Sorry, there should be a C. So calculate angles. Let's calculate angle C in ACD. What would angle C be? Angle C, we would take 180 minus 45 minus 30. So 180 minus 75 is 105. So angle C is 105. Okay? And since these other two, we automatically know that D is going to be 105. I wouldn't even have to label this as 30 and 45. We just know they're congruent, right? They were congruent. This one was congruent to that. These two were congruent. So we automatically know that that third angle is 105 in the other triangle. Everybody get the idea? All right. Theorems. Same set of theorem we've been using before. Now we're applying them to triangles. If a triangle is congruent to itself, if we say a triangle is congruent to itself, and it's in the same order, ABC is congruent to ABC, then that's called reflexive property of congruent triangles. You just can call it reflexive. If we have two triangles that are congruent, and we switch the order, if we say ABC, triangle ABC is congruent to triangle DEF, and we switch it around to say triangle DEF is congruent to triangle ABC, that's symmetric property. And then finally we have transitive property. Same idea as when we used it with addition and that type of thing, and equality. If ABC is congruent to DEF and DEF is congruent to JKL, we can say ABC is congruent to JKL. ABC and JKL are both congruent to DEF, so they're congruent to each other. That's transitive. Everybody have it? Looks like you're still writing. Everybody have it now? Okay. Here's a proof. So in the triangle, we're given ABD is congruent to CDB, and ADB is congruent to CBD. AD is congruent to BC, and AB is congruent to DC. So that's, as marked, it is given. That's our first step in our proof. How do we know BD is congruent to itself? What property is that? Go ahead. That's reflexive. That would be a reflexive property. What do we know by the third angles theorem? The third angles theorem says that if two angles of a triangle are congruent to two angles of another triangle, their third angles are congruent. So what could we say here by the third angle theorem? Do we know that two angles in the one triangle are congruent to two angles in the other? We do. So what's our third angles? Megan? What would our third angles be? I'm not sure. Caleb?
Angle ABD is congruent to angle CDB.
We already know that. That's given to us. What are the unmarked angles? A and C. Those are our third angles. Right? These are the third angles. We know, we can say that A is congruent to C because of the third angles theorem. So angle A is congruent to angle C. That's what I can say by my third angle theorem. And then now we have all 6 parts of the triangles are congruent. The 3 sides are congruent. 3 of the angles in each one are congruent. So now we can say the triangles are congruent. What would that be called? Okay, that's our definition of congruent triangles, that all the sides are congruent. So we would call that last step definition of congruent triangles.